Now next we consider moving veins. Previously we only consider the structures or veins or blade, those were stationary at rest, and the fluid strikes them and we calculated the forces. Now we consider the cases of moving veins. Clear? So here both the bodies are in motion, means the fluid and the body that it strikes, for example vein or blade. So then in that case we have to consider the absolute and relative velocities. Clear? Now in this case we show in these diagrams the different relative and absolute velocities, and we want to establish the relationship between them, because earlier we saw that when a fluid strikes the body, so at the inlet and at the exit we are interested in the triangles. You saw here that we make the triangles here. What is the situation at the exit, and then what is the situation at the entrance. Now in this case, for example, it is possible that the body is inclined. Clear? Let's say it is like this. So it means that the fluid enters over this vein or blade at an angle, and then it leaves this object at an angle. So in this case, if we are interested to calculate the forces, then we have to resolve these into different components, like we resolve this V2 into components. So similarly, if the body is in motion, then in that case we have to consider the relative velocity concept. So this is what we are going to study here. Before we consider the relationship between the relative velocity, the absolute velocity, and the velocity of the body, first we define them. That the absolute velocity v, we will denote this by v. This is as per our textbook. So the absolute velocity v of a body is its velocity relative to the earth. Whenever the body is moving with respect to the earth, that is its absolute velocity. The relative velocity, which we denote by this small case v to differentiate, of a body is its velocity relative to a second body. So relative to a second body, the relative velocity we will denote by this notation here. This is small case v, not nu. Actually nu we use for kinematic viscosity. Clear? Also we use it for specific volume, but in here it is the same notation, but it is the relative velocity. Clear? We will say it is a small case v. So this will be its relative velocity relative to a second body, which may in turn be in motion with absolute velocity u relative to the earth. Clear? So what it says that you have a body, first body here, it moves with a velocity of 100 meter per second. It moves with a velocity of 100 meter per second. We have another body, second body here. Clear? This is second body. It moves with a velocity of 40, let's say 40 meter per second. Second body moves with a velocity of 40 meter per second. So what is the relative velocity of the first body with respect to the second body? Difference of the two. Clear? That will be equal to what? 60 meter per second. This will be the relative velocity with which this body, first body, is moving with respect to the second body. So this is what? This relative velocity is here. This is here. If the second body can move with 60 plus 40, both will have the same speed. So that's why we can say that the absolute velocity v of the first body is the vector sum of its relative velocity relative to the second body and the absolute velocity u of the latter. What it says that this is v is equal to u plus the relative velocity v. This we can write down as the vector sum. This is what I show here. This is your v, and the second body is moving with a velocity u, and the relative between the two, that is what? That is your small case v, the relative velocity here. First body is moving with a velocity 100 meter per second. Second body is moving with a velocity 40 meter per second. The relative velocity is 60 meter per second. So that 40 plus 60, that is 100. So what we can say is that the absolute velocity of the first body is the vector sum of its relative velocity with respect to the second body and the absolute velocity u of the second body. So we can write down v is equal to u plus the relative velocity. This is the relationship between these three velocities that shown here. V is the absolute velocity of the first body, u is the absolute velocity of the second body, and small v is the absolute relative velocity of the first body to that of the second body. Clear? So if this thing is clear, then for each of this triangle which can form, because I said that the body and the fluid, they will interact, and we are interested to calculate the forces. So now that the body is also in motion, we will consider the concept of absolute and relative velocities. Clear? Let us, before we discuss that, let us define that this alpha and beta is the angles made by the absolute and relative velocity of a fluid, respectively, with the positive direction of the linear velocity u of some point on the solid body. So in this diagram, what you see is that, let's say we have a vein, the fluid is coming and it is entering this vein, and then it flows over the vein, and then it leaves the vein. So that's why there can be an inlet velocity diagram and outlet velocity diagram, and the vein is moving with a velocity u. This is what it means, the linear velocity u in the x direction. This is what we are assuming, u. Clear? So the vein is moving with a velocity. If the vein is stationary, the fluid can enter at an angle, leave at an angle, and you can calculate xy component as we did in this example here. But if the vein is in motion, then the situation will be different from here. We have to consider the relative velocity concept also. So before we discuss that, we want to establish the relationship between these here. This is for the linear case. When you have a linear case here, then this is the relationship between the three velocities. Clear? If these velocities, they make triangles, then what will be the relationship with this? Clear? What I say is that when we have the velocity in x direction, this is v. But if the velocity makes an angle theta, then it has two components. Clear? Then the same velocity has two components. So now in here you can see that the velocities, they make component, the absolute velocity and the relative velocity. They make angle here, because for the cases that we will discuss and calculate the forces, you can have this triangle, you can have this triangle, you can have this triangle. You understand? And then from here you have to calculate the relationship between the velocities. So now we want to say that if we have this situation, what will be the relationship between the velocities for xy directions? This is what we want to calculate here. So let us define that alpha is the angle which is related to absolute velocity of the first body. The second body, which is a vane or blade, that has only just linear velocity u, not making any angle. But the relative velocity between the two, that can make an angle theta that we denote by beta. That can make an angle theta, and that we denote by beta. So now we are interested to calculate the relationship between the three velocities in parallel direction to u, parallel to u, and perpendicular to u. Perpendicular to u, what is the relationship between these three velocities? This is what we want to calculate. If there is no angle theta, then the relationship is simply this one. Absolute velocity of first body is equal to absolute velocity of second body plus their relative velocity. Then this is the simple relationship. But if the velocities are such that they make angles, then in that case, what is the relationship that we want to establish? Parallel to the u direction, direction of second body movement, and perpendicular to the u. What will be the components of these two? This is what we want to calculate. Clear? So for all the three cases, if we proceed, then in that case, we will say that perpendicular to u, clear, this will be equal to, this is actually the parallel notation. This one which is used, this is the parallel notation. So parallel to u, this is the relationship between the two. But since they make an angles, so now vu will be equal to v cos of alpha, and this vu, it will be equal to v cos of beta. And because u is linear, it will remain as u. And perpendicular to u, this is u, perpendicular to u, then we have the normal component Vn. This will be equal to the relative component Vn, and will be equal to V sine alpha is equal to the relative velocity sine beta. Because there is no component perpendicular to u, it is linear, so that's why u is 0. So then in that case, V sine alpha will be equal to V sine beta. Now these two components remain the same for all this. For this you can calculate, you will get these components. For this you calculate, you will get the same result. For this you calculate, you will get the same result. So that's why it says that whatever is the shape of triangle, you will always, this relationship will be applicable. That v cos of alpha will be equal to u plus small v cos of beta, and v sine of alpha will be equal to small v sine of beta. Whatever is the shape of triangle, at the inlet, at the exit, whatever is the shape here, whatever is the shape here, any of these triangles can come here and form the shapes. Depending on the flow conditions, we will always find the answer that this will be applicable for all the three cases. Now let me just prove for two cases, you can verify for the third case. Clear? How that these components are applicable to all the three cases. So whatever is the shape of triangle, this will always be the case. That's why for all cases, these will be the components. And this then we can use to calculate the forces. So let me just do it for one or two cases, and then you can do it by yourself to verify that these components will hold for all the three triangles. Okay, so now let us come to this first figure. Now we come to this first figure. So in the first figure, what we have is that V, it makes an angle theta. So you see we have V cos of theta. Clear? What we will have, let me redraw and show these components here. Now you can see here we need to just resolve these into different components. Now in this case, this V makes an angle alpha. So that's why it's one component. It will be, if I can show here, it's one component that will be equal to V cos of alpha. This will be equal to capital V cos of alpha. Clear? This is V. And one will be its vertical component here. And what will be this component here? This component will be equal to V sine of alpha. Now we have the relative velocity. So the relative velocity make an angle beta. So then in this case, if I use another one here, so then in that case, one is this component here. What will be this component? It will be small v into cos of beta. So this will be small v into cos of beta. And one is this component here. This will be equal to small v into sine of beta. Into sine of beta. Clear? So now from the figure, what is Vu? From the figure in this direction, you can see that in the direction perpendicular to you, what is the situation here? So you can see that perpendicular to you, what is U? U is the motion in this direction. What we have? We have, you see, these two components must be the same. So what we can write down here is that V sine of alpha is equal to small v sine of beta. You can see here these two components, they are the same. See, look here. So that's why we can write down V sine of alpha is equal to small v sine of beta. Now parallel to u, then in that case what we have? We have V component in the u direction. So you see this is in the u direction. This is equal to u. This is equal to what? From here to here is u. So this is equal to u. And then from here to here, this is the u component parallel to u of the small velocity. Let me make it small. This is equal to small velocity in the u direction. So what is Vu? In the u direction, V cos of alpha. So this is equal to V cos of alpha. U has component in this direction, so this is u. And what is the u component of small v? V cos of beta. So this is equal to V cos of beta. So now from here what you can see is that in this case perpendicular to you, this is the component, and parallel to you, this is the component. This is what we saw here. You see here, parallel to you, V cos of alpha is equal to u plus small v cos of beta, and perpendicular to u, v sine of alpha is equal to small v sine of beta. This is what you saw here. So you see, for the first case, we have these two relationship in the parallel and perpendicular directions to u, correct? Okay, now let us come to the second figure, that we have the same relationship or not. Let me remove this. We come to the second figure to determine what is the relationship between these three velocities here. Now let us come to the second case. Then you can verify yourself for the third case. So now in the second case here, this small v, which is the absolute velocity, minus u, that is the relative velocity, that makes an angle of beta. Now beta here is this, and v makes an angle of alpha here. Clear? So now in here, if I draw the line, so you can see that this is vu, component of the absolute velocity in the u direction. This is vu. Clear? And what is vu? V cos of alpha, same like before. This will be what? From here, this will be equal to v cos of alpha. V cos of alpha. Similarly, in the vertical direction, we will have this component here. From here, you see this component here. This will be equal to what? This will be equal to v sine of alpha. This will be equal to v sine of alpha for v. So now for v, it is clear. V cos of alpha and v sine of alpha. Clear? Now in here you can see that this angle, if I want to resolve this angle here, this angle will be 180 minus beta. This angle will be equal to 180 minus beta. So this angle is equal to 180 minus beta, correct? Now in the u direction, parallel to u, this is parallel to u. So what we have? We will have in this direction vu, that will be equal to u. U is now from here to here. What is u? U is from here to here. This is u. From here to here, this is u. So now we have u. So vu will be equal to u minus small velocity cos of 180 minus beta. This will be equal to cos of 180 minus beta. You see this component, this will be equal to u minus, this is in opposite direction, u minus v, small v cos of 180 minus beta, correct? So now in this case, what we can write down is that this cos of 180 minus beta, what we can write down, cos of 180 minus beta. So you already know previously that cos of, you studied in mathematics, cos of alpha minus beta. So cos of alpha minus beta, that is equal to cos of alpha cos of beta plus sine alpha sine beta. If you remember this, so now in this case we have alpha equal to 180 degree. So now cos of alpha 180 degree, that is equal to -1, and sine 180 is 0. Clear? So this term is 0, sine 180 is 0, so this becomes 0. Cos of 180 is -1, so this is equal to minus cos of beta. So it means this term is then equal to minus cos of beta, because cos of alpha 180 is -1, so minus cos of beta. So now it means that this cos of 180 minus beta is equal to what? It means that this cos of 180 minus beta, this is equal to minus cos of beta. This is equal to minus cos of beta. So what we can write down here is that Vu, and what is Vu? V cos of alpha. This is capital V cos of alpha. This will be equal to U minus into minus cos of beta into this small velocity V. So now minus into minus plus. So what we are left with, it means that V cos of alpha, that is equal to U plus small v cos of beta. And this is what we obtained for case 1. This is what we obtained for case 1, parallel to U. Clear? This is what we obtained for case 1. Now for case 2, perpendicular to U, the component here. So perpendicular to U is what? This will be equal to V sine of alpha. You see perpendicular, so these components are then the same. We have V sine of alpha this must be equal to small v sine of beta. Clear? Because in this case this will be equal to sine. This will be equal to what? This will be equal to this component here for small case. This will be equal to v into sine of what? This will be equal to sine of 180 degree minus beta. And you already know that sine alpha minus beta, this is equal to sine alpha cos beta. This is equal to sine alpha cos of beta plus minus, in this case minus. So this will be equal to minus cos alpha into sine beta. So now when alpha is 180 degree, so you see cos of sine alpha, this is 0, this term is 0, and cos of alpha is 180 degree minus 1, when this is so minus, so minus into minus 1 into sine of beta. So minus into minus sine beta, that's why this term can be written as v into sine beta, v into sine beta, and that's why this v into sine beta, that is written here, v into sine beta. So now you can see that these are the same relations that we obtained for case 1. For case 1 and case 2, we obtained the same relations. Clear? So that's why whatever is the shape of triangle, you will always get these same expressions. You can see here, for all cases, v cos of alpha is equal to u plus v cos of beta. See, for the second case, we get that relationship. And perpendicular to u, v sine of alpha is equal to small v sine of beta. See, we get this relationship. So that's why whatever is the shape of triangle, you will always get these relationships. These relationships are true whatever is the shape of triangle. Now you can verify by yourself for the third case. You will get the same result. For the third case, you will get the same result. That's why we say that whatever is the shape of triangle, for all cases, you will get this same relationship. You can verify yourself for the third case. I verified it for the 2 cases. Clear? Okay, so now force of a jet on 1 or more moving vanes or blades. Now in this case, we want to calculate the force of jet on 1 or more moving vanes. Clear? So what will be the force? First, we consider a single blade or vane moving parallel to jet. So we consider a single vane and it is moving parallel to the jet with a velocity u. Here, see, we have the velocity u. So now there are 2 major differences between the jet action on a stationary object and on a moving object. The first thing is that the amount of fluid that strikes a single moving object must be different from that which strike a stationary object. So it means that when the fluid which is hitting a stationary plate and then a fluid which is hitting a moving plate, that is different. Clear? The second difference is that for a moving object, we must consider both relative and absolute velocities, which makes determination of delta V more difficult. Clear? What was the case that if you want to calculate the force, so now the force is equal to rho q into delta V. So now for the case of moving vane, how we calculate this delta V? Clear? So this is now challenging. The first thing is that the discharge which is hitting the vane, that is different from stationary vane. And the second thing is delta V calculation, because we have to consider the relative and absolute velocities. So what we do is that if the cross-sectional area of the jet is A1 and its velocity V1, the rate at which the fluid issues from the nozzle, that is equal to, this is the mass flow rate, m with a dot. This is rho q. So this is the fluid which is coming from the nozzle. It will hit this plate. Clear? Now the amount of fluid that strikes a single moving body per unit time will be less than this if the body is moving away from the nozzle, and more than this if it is moving towards the nozzle. It means that you see you have a body and we have a jet of water which is striking this body. So if it is stationary, clear, it means it is stationary u is equal to 0, this fluid, this much will hit this vein, this body here, this plate held perpendicular to this jet. But if the jet is moving, so it says that the fluid is coming with a mass flow rate this much, but the fluid is in motion because it cover a distance. U is now here. In 1 second it cover this distance. Clear? It comes here because it is moving now with a velocity small u. So that's why the discharge which is hitting this vein will be less than here. Why it will be less than here? Because some of the fluid is used to cover this distance and the remaining will hit this vein. You understand? So that's why the discharge that is striking a single moving vein, that will be less than if it is a moving. Clear? That will be less if the body is moving away. So in that case, this is the situation when the fluid strikes a stationary vein, it hits with this discharge. But when the body is moving, the discharge hitting the vein will be less. Why? Because you can see here, if the body reaches here and the fluid is stationary, then the fluid is not able to hit the discharge. So if the body is here, then it will be able to hit this body, but it will be less than the absolute. Clear? So if it is moving with a velocity u less than that of the jet, if u is less than that of the jet velocity v, then it will hit the plate. But if this body is moving with a velocity equal to or greater than v, it will never hit this plate. For example, one body is moving with 100 meters per second, and it wants to catch another body which is also moving 100 meters per second. Will it catch the second body? No. Will it catch this second body? No. If it is moving with greater velocity, can never catch it. But if this body is moving with 100 meters per second and the second body is moving with 60 meters per second, it can catch. It can catch 60 meters per second body. So that's why u is less. U should be less than that of the jet. Then in that case, the fluid that will strike will be proportional to the difference between the two velocities. Clear? The body is moving with a velocity 60 meters per second. This is moving with a velocity 100. So the difference of the two, that will be striking. Clear? So it means that v1 minus u is equal to nu1, the relative velocity. With this velocity, the fluid will be able to strike the plate. With this velocity, it will be able to strike the plate. So if we have the cross-section area of the jet as A1 and the velocity of the jet V1, then the rate at which the fluid issues from the nozzle in terms of mass will be this much, Q dash. This is now the relative discharge. And instead of V1, it will be equal to A1 into V1 minus U. And what is V1 minus U? It is actually your relative velocity. So it means that this discharge will be able to hit the vein, not A1 V1, not A1 V1. This will not hit the vein because the vein is moving. If the vein is stationary, it will hit with this discharge. But since the vein is moving, then the discharge that will hit the vein will be in terms of relative velocity. As I explained here, the body is moving with 100. The first body is moving with 60 meters per second. So what will be the velocity with which this body will catch this? The difference of the two, 40 meter per second. Clear? So that's why in here, this will not be the case if we have moving plate. But this Q dash, this is the discharge which will hit a single moving vein. And this new one, this small v1, this is equal to v1 minus u. This will be the case if the vein is stationary. So this will be that case. If the vein is stationary, it will hit with this discharge. But if the vein is moving, it cannot hit with this. Means the discharge will reduce. Similarly, the mass flow rate, that will be equal to rho q dash, given by this expression here.
Sir,
now yes,
sir, jet और वेन में क्या फर्क है?
jet is this is the jet of water. अभी तक आपको ये समझ नहीं आया? This is the jet of water and this is the vein. This is your vein. So this jet of water, it strikes this vein. Is it clear now?
सर अगर वो लीनियर हो तो उसे हम जेट कहेंगे और
No.
अगर वो
No.
जी
Jet of water is just a free stream of water. आपने अगर आपके पास ये टैंक है, आई एम एक्सप्लेनिंग व्हाट एंड यू आर स्टक इन व्हाट. दिस इज द प्रॉब्लम. मैं क्या समझा रहा हूँ और आप लोग कहाँ फंस गए? दिस इज नाउ ओरिफेस and this is a free jet which is coming from this orifice. This is also a jet. आपने प्रैक्टिकल में नहीं पढ़ा orifice and jet apparatus? So where we say it has two components. Jet is just a free stream of liquid which is flowing out. This is jet of water. This is jet of water. अभी समझ आ गई?
जी सर, जी सर.
Okay, so now considering the relative velocity, now we consider the discharge. That the discharge hitting a moving vein will be less if the vein is stationary. If the vein is stationary, it will hit with this discharge. But if the vein is moving, it will hit with a discharge less than this. How much? V1 minus u. Why? I give you the reason. Because if the vein is here, so it hits with a velocity at this point here. But if the vein is here, so it will hit, the nozzle is fixed. This is not moving, this is fixed. So the vein is moving. When the vein reaches here, because it is moving with a velocity u, then it says that this much discharge, clear, it will be used to elongate the length and the remaining will hit. And what is the remaining that will hit? V1 minus u. Clear? So this will be the discharge that will hit. Clear? So this you have to use in the equation, V1 minus u or small v1. Clear? Okay. So now that we consider the change in velocity, so now this change in velocity, we have to consider the relative velocities. So for the inlet and for the outlet, this is the relationship, and we find out that this delta u, this is equal to small delta u. Clear? This is a very simple proof. It is given, you look to the textbook. These are given along with this diagram here. And this is a very simple proof. Otherwise, even for the triangles, we can prove this. You consider these triangles as I did here. In this case, you see for case 1 and case 2. Similarly, we can proceed and we can prove that this delta v is equal to change in velocity in the u direction. That is equal to absolute velocity is equal to change in the relative velocity in the u direction. So that's why in the equation for force, you consider delta v or small delta v, you will get the same answer. Clear? You will get the same answer. But this change in relative velocity is easier to obtain, so you will prefer to use this in the problems. But you use capital delta V or small delta V, you will get the same result. Clear? This is a very easy proof that is given in our textbook. So now we say that summation of forces that will be equal to rho q dash delta V or rho q dash delta small v. If you want to calculate the force on a single moving blade, this will be equal to rho q dash, where q dash is the discharge less than the for that stationary vane that we just discussed. Clear? Into either you take change of absolute velocities or change of relative velocities, you will get the same answer. So this is the equation that you can use to calculate the force on a single moving blade or vane or plate. Clear? So we are mostly interested in the force exerted in the direction of the jet, which we previously named as u or x direction. So for u component of the force, Fu will be equal to rho q dash into delta Vu or rho q dash into smaller relative change in the velocity in the u direction. So this is now the equation that we will use to calculate the force on a single moving vane. Clear? What is the difference with a stationary vane? The discharge is reduced if it is moving away from the jet of water, and we consider the relative velocities. This is the difference between the force acting on a moving vane as compared to the stationary vane. We will solve a problem, it will be further clear to you. Clear? Similarly, we can use this expression, and q dash will be equal to a1 into small v1, because this is equal to capital V1 minus u. So for us, this you can also use to calculate the force in the u direction acting on a single moving vane. Okay, if we have a series of rotating vanes instead of a single vane, if we have a series of moving vanes, this is practical case, because a single moving vane, this cannot be practically case. Where we can consider a practical case where a single moving vane, and we are interested to calculate the force on that. Clear? So rather we are interested in a series of moving vanes coming to the practical case. So in that case, for a series of moving vanes, a stream of fluid striking, impinging on a single moving vane, as we discussed, occurs rarely. More commonly, the jet is directed as series of closely spaced rotating vanes or blade, as in a turbine. In a pump, we have a series of moving vanes. You can see here, this is a hydroelectric power plant. We have a turbine here. This is a turbine. So in this turbine, and an example is a Pelton wheel, we have vanes that is on this wheel, and the jet of water which is coming, it is striking these vanes and it rotates this wheel, turbine, and then this turbine rotates, and this turbine is connected with a generator, and we generate electricity. Clear? So this is the interesting case, that rather than a single moving vane, we have a series of moving vane. And same is the case for a pump also. If you see in a pump, we have a series of blades which are connected to the rotating element. Similarly for a turbine here. So then in that case, you see the jet is striking the vane or blade, and it rotates this wheel, and this turbine converts this hydraulic energy into rotating shaft mechanical energy, and then it is connected to generator. Generator converts mechanical energy into electrical energy. So in such cases, when a jet hits a series of moving vanes, whatever the flow does not strike the first vane will strike the second one, and so on around the circle. So as a result, for a series of vanes, we use the full momentum transfer rate. It means that this is not q dash, but rho q equal to rho a1 into v1, not q dash. We do not consider for series of moving vane q dash. This was the case for a stationary vane. Whatever is the fluid coming, the hole is striking the vane. Then we consider if the vane is moving, the hole will not be able to strike the vane. V1 minus U, that will be able to strike the vane. Clear? This will be able to strike the vane, this one here, V1 minus U, because the vane is moving, so the jet will elongate to hit. So that's why the discharge hitting the vane is reduced. But if it says that if it is a series of moving vane, it says that if this vane comes here, although the discharge has reduced, but at the same time the next vane has come, so the discharge which will not hit this vane, it will hit this vane, and so on. That's why it says that for a series of moving vane, if it does not strike the first vane, that will strike the second one, and so on. You see, if some of the fluid is not able to hit this vane here, the next vane will come here and it will hit. So it means that the discharge hitting the vane is not reduced. It was reduced for a single vane. Because if this vane is moving and it misses some discharge, the second would come. This is how design will occur, that we have to provide the vanes in such a way that if the discharge misses one blade, the second will come and it will hit that discharge. So that's why we do not use Q dash, but we say for a series of vane, the same discharge we consider in calculating the force. Clear? Thus we can express the U component of the force on a series of vanes is this. So now if you consider this with the previous case, this is the same, this is the same, this is the same, this is the same, but there what we use? We use only relative velocity because the discharge hitting the vane is less. But for a series of vanes, it is the same discharge, V1, it is not reduced. So this is how we are able to calculate the force on a single moving vane and on a series of moving vanes. So let us finish this chapter by solving this problem here. Now in this case what we have, that we have a single moving vane. So we have a 2-inch diameter water jet with a velocity of 100 foot per second. It strikes a single vane moving in the same direction at a velocity of 60 foot per second. So now the velocity of the jet, which is circular in cross section, is 100 meter per second and the vane is moving with 60 foot per second. Clear? Friction losses over the vanes are such that V2 is the exit velocity, relative velocity is 0.9 times V1. It means that the velocity that enters into the relative velocity that enters into this vane, because 100 minus 60, 40, with this velocity the fluid enters because the vane is moving. If the vane was not moving, what will be the entering velocity of the jet? 100 foot per second, as in the stationary vane we considered. So since the vane is moving, that's why the fluid will enter with a relative velocity 40 foot per second, because it moves over this vane, so there is friction. So it says that the exit velocity, relative velocity V2, this is the relative velocity. Clear? So in this case what is happening is that this velocity is 0.9 times the V1. So due to the friction there will be some loss of velocity, that is now 36 foot per second as the fluid moves over this vane. Another thing here I need to explain is that in this diagram you see here the relative path and the absolute path. This is important that you need to understand the relative path. So you see here this jet, if it is flowing, it will follow this path. Clear? This is the absolute path. So the velocity which is shown here is absolute velocity. You bring it here parallel to this to complete the triangle. So you see this velocity we slide here and bring it here to show the exit velocity triangle, correct? Now in this case, what appears? The relative path. This is the relative path, because what appears to us is that the jet of water moves in this path here. So it means that this is the relative path, clear? This is the absolute path. So the absolute path followed, we have the absolute velocity, clear? And this is the relative path. So that's why the fluid exits with the velocity that is relative velocity, because it follows the relative path. So then we consider this triangle that we saw earlier in this case is for different conditions here. Either we can have this condition, we can have this condition, we can have this condition, depending on the given situation. So that's why we show the relative velocity here, relative path. Absolute velocity, absolute path, that is shown here. And this triangle you consider in calculation of the forces. This one here, now the jet enters horizontally, so that's why there is no triangle. But it can enter horizontal at an angle. Then in that case, we will have triangle similar to this one, more complex case. But now the fluid enter horizontally, so that's why the inlet velocity diagram is easy. But at the exit, then we have this triangle here. So let us solve a problem how we calculate the forces. So now the velocity vector diagram at the entrance and at the exit, they are given. This is the velocity diagram at the entrance. You see v1 is equal to u1 plus small v1, and this is the exit velocity diagram, clear? This is the absolute path, this is the relative path, and this is the motion, the linear motion in the x direction, that of the vane is moving with this direction. So it means that this will be your alpha and this will be your beta, the two angles which the relative and absolute velocities make, as we discussed earlier. Now we have v2 is equal to 0.9 times v1. So v2, the small velocity, v2 relative velocity, we can calculate 36 foot per second. Now earlier we studied that whatever is the shape of triangle, we saw three conditions. Whatever is the shape of triangle, v2u, that will be equal to v2 cos of alpha 2 plus u plus small v2 cos of beta 2. This condition is true whatever is the shape of triangle, earlier we discussed. So you plug in the values and this is 28.8 foot per second. And in the vertical direction, then v2 sine of alpha 2 will be equal to small v2 sine of beta 2. Whatever is the shape of triangle, these relationships are always true. So in that case, this is equal to minus 18 foot per second. Clear? The negative will only show the direction. Clear? Now we calculate q dash because we have a single moving vane. So a single moving vane, the discharge hitting the vane will be less. Clear? This is what we discussed earlier. So we consider q dash, and q dash is equal to a into small v1 or a1 into difference of v1 minus u. The relative velocity you have to consider. Clear? So in this case, these values are given to us. So this is the discharge. So now force in the x direction, we consider the force in the x direction here. This is the assumed direction and this is the assumed direction. The plus minus sign will tell us that these assumed directions are correct or not. So now we consider and try to calculate these forces. Clear? We try to calculate these forces here. So in this case, we calculate this force minus fx here, minus because this is opposite to plus x. So that's why we have minus, there is no other force. So rho q dash into delta V. So this is equal to, you just put the values, this is equal to minus 120.4 pound. So you get plus answer, because this minus cancel out with this minus, you get plus answer. So it means that the force on the vane on the water is to the left as assumed. Hence the force of water on the vane is 120.4 pounds to the right. So this is the correct for the vane on water. The force of the water on the vane will be opposite to this. Next we consider in vertical axis. So that will be equal to again minus y, because this is opposite to the plus y. So then in that case we consider minus y, no other forces to consider, only just this component rho q dash into change of velocity in the normal direction, in the y direction. So you plug in the values, minus 30.4. So again we get plus. It means the assumed direction for Fy is correct. Clear? And the force of water on the vane is equal and opposite to this direction, means upward. So the force of water, this will be, you use Pythagoras theorem. This will be force of water on blade or vane, that will be equal to, by Pythagoras theorem, this will be equal to Fx square plus Fy square. You will get this result. And the angle you can calculate. You can easily calculate from these components the angle. The second part of the question is, if this vane were one of the series of vanes, then what will be the force? So if it is a series of vane, then instead of q dash, it will be q, because all of the discharge will hit the vane. If it miss one vane, it will hit the second coming vane. So that's why for a series of moving vane, we calculate q, not q dash. So you see the discharge is 2.18. This will hit a series of moving vane. What was the discharge hitting? 0.843. It means the discharge hitting a single moving vane is less, 0.87. And here this is 2.18. So for a series of moving vane, the discharge hitting the vane will be more. Because if it miss the first vane, the remaining will hit the second vane. So it means the full discharge is utilized for a series of blades. So then in that case, Fx you can calculate now with q, not q dash. So this one here, and because it says to find the horsepower transfer to the vanes, it means in the u direction. So that's why we only calculate the component in the u direction, which is Fx. And what will be the power transfer? Force into velocity. This is what we studied before. Force P will be equal to F into U, force into velocity, divided by 550 in horsepower. So this is the power transferred in U direction to the series of moving vanes. Clear? Now coming here, the forces that we calculate in the first part. So we stated that this is the diagram here. So we calculated this is the force Fy and this is the force Fx in the first part. So the force of the jet on this vane will be opposite to this. So it will be in this direction here. This will be the force of the blade on this moving vane, and similarly this direction was correct. So it means that the force of the jet on that will be in the vertical direction here. So this force will be acting here in vertical direction, just equal and opposite to that. And then the resultant that you can calculate, that will be acting in this direction. the resultant force of blade on this force of water. Force, this is equal and opposite. So this will be force of water on this vein or blade. Clear? This will be force of water on this vein or blade. And you can calculate the alpha. Clear? This alpha you can easily calculate. Clear? This is what you saw here in this diagram here. You can see here. So this is the same. Either you consider here this as alpha or this as alpha, alternate angle, same. So you can easily calculate. So this is how we calculate forces on stationary and moving vanes.